Hi, Questers. Today's quest begins with a simple, everyday decision that seems trivial but is actually a matter of survival physics. Every morning, your outfit choice affects how your body interacts with the sun. What feels like a simple style decision is actually you engineering a personal microclimate guided by the laws of thermodynamics.
Let us simulate 4 scenarios you have likely experienced. Scenario 1, a scorching summer day. You wear a dark, heavy shirt and instantly regret it. The heat clings to you, penetrating your skin. You feel trapped in an oven, absorbing every ounce of the sun's punishment without relief.
Now, scenario 2. On that same sweltering afternoon, you switch to a white linen shirt. The difference is profound. You feel a sudden relief, as if you have engaged a protective shield. The oppressive weight vanishes, and you are no longer fighting the atmosphere. You are surviving it. Scenario 3 takes us to the freezing depths of winter. You stand in the biting cold, but wearing a dark coat in a patch of sunlight. Suddenly, that faint light acts as a lifeline. You feel thermal energy soaking into the fabric, effectively warming you against the hostile cold. Finally, scenario 4. You stand in that same winter sunlight, but wearing a bright white jacket. The warmth you desperately need seems to bounce right off. The sun looks powerful, but its heat feels distant. You are left shivering, wondering why the universe is suddenly withholding its energy. So here is the fundamental question that drives this entire mystery. The sun overhead remained constant. The ambient temperature of the air did not fluctuate. The only variable in this equation was the dye in your fabric.
Why does a simple shift in the visible spectrum alter your physical reality so drastically? Before we unlock the physics, pause this video for a moment. Try to connect the dots and drop your best guess in the comments below.
To understand this, we must first dismantle a common misconception about the nature of light itself. We tend to think of color as a purely visual experience, something that exists only for art or beauty. But in the laws of physics, color is a functional description of how matter interacts with energy. Sunlight is not just brightness. It is a bombardment of electromagnetic radiation, carrying massive amounts of energy in the form of photons. When this torrent of photons travels 93 million miles and finally strikes your clothing, 3 things can happen. The energy can be reflected, bouncing off like a rubber ball. It can be transmitted, passing through the material like light through a window. Or, most critically for our quest today, it can be absorbed. This third option is where the magic and the danger truly lies. This is where light transforms into heat. Let us look at the color black. To your eyes, black is simply the absence of light, a void where color should be. But to a physicist, a black object is a hungry entity. It is a material that refuses to reject the energy coming toward it. When you wear black, your clothes are telling the universe that they accept every wavelength of visible light that hits them. They do not discriminate. They take it all. This brings us to the atomic level. When those photons are absorbed by the dark dye in your shirt, they do not just disappear. The law of conservation of energy states that energy cannot be destroyed. It can only change form. The absorbed light energy is converted instantly into kinetic energy. It causes the molecules in your shirt to vibrate violently. In the language of physics, molecular vibration is exactly what we call heat. This is why the dark shirt in summer feels like a torture device. You have wrapped yourself in a material that is actively harvesting energy from the sun and converting it into thermal vibration directly against your skin. You are essentially wearing a solar panel that generates heat instead of electricity. The shirt is doing exactly what physics demands of it. It is maximizing the transfer of energy from the sun to your body. Now, consider the color white. A white object is the polar opposite, acting as a mirror to the universe. Instead of absorbing the incoming photons, the molecular structure of white dye repels them. It reflects the entire visible spectrum, mixing them back together to create the white light you see. By reflecting the radiation, the material is refusing to participate in the energy transfer. It sends the heat back out into the environment. This explains the relief of the white shirt in summer. You are literally rejecting the thermal load that the sun is offering. Ancient civilizations understood this intuitively long before modern thermodynamics. Look at the architecture of the Greek islands or the coastal cities of North Africa.
The buildings are painted stark white, not for decoration, but for survival. They are designed to bounce the punishing solar radiation back into the atmosphere to keep the interiors cool.
However, this story has a twist that most people miss, and it involves a concept called black body radiation. In physics, an ideal black body is an object that absorbs all incoming radiation. But here is the catch. A perfect absorber is also a perfect emitter. This means that while black objects are great at soaking up heat, they are also incredibly efficient at releasing it. This leads to a fascinating paradox in how we use color. If you touch the hood of a black car on a sunny day, it burns your hand because it absorbed the solar energy. But if you come back to that same car at night, after the sun has set, you will notice something strange. The black car will likely be colder than the white car parked next to it. Because it is a better emitter, it radiates its stored heat out into the cold night air much faster. This phenomenon is known as radiative cooling. It is the reason why the asphalt on the road cools down rapidly after sunset, and why dark rocks in the desert become freezing cold at night. The same property that allowed the object to get hot quickly also forces it to lose that heat quickly when the energy source is removed. It is a double-edged sword of thermodynamics. High intake implies high output. This principle is used in high-level engineering. Consider the SR-71 Blackbird, the famous spy plane. It flies at 3 times the speed of sound, creating immense friction heat with the air. It was painted black not just for camouflage, but because the black paint helped radiate the internal heat produced out of the airframe more efficiently than any other color. In the vacuum of space or the thin atmosphere, emission is the only way to cool down. This brings us to a puzzling real-world example that seems to contradict everything I just told you. If black absorbs heat, why do the Bedouin tribes in the scorching Arabian desert wear flowing black robes? It seems like suicide by thermodynamics, but scientists have actually studied this. The answer lies in the combination of physics and geometry. Yes, the black fabric gets hotter than white fabric would. Much hotter. However, the heat absorbed by the black robe heats the air inside the robe. As we know, hot air rises. This creates a miniature updraft between the robe and the skin. As the hot air escapes through the fabric, it sucks in cooler air from the bottom of the robe, creating a continuous cooling breeze across the skin. The black color powers a personal convection engine. It turns the heat into air movement. This proves that physics is rarely a single variable equation. It is a complex dance of absorption, emission, and convection. But let us zoom out from the human body to the planetary scale. The Earth itself plays this game of colors. The polar ice caps are bright white. This high albedo, or reflectivity, bounces sunlight back into space, helping to keep the planet cool. It is the Earth's white t-shirt. But as the climate warms and the ice melts, it reveals the dark blue ocean underneath. The dark ocean absorbs more sunlight than the white ice did. This warms the water, which melts more ice, which reveals more dark ocean. This is a positive feedback loop, a dangerous cycle driven entirely by the changing color of the planet's surface. The physics of color is quite literally deciding the fate of our global climate. We also see this in our cities. We call it the urban heat island effect. We have paved our natural world with black asphalt and dark concrete. These materials absorb solar radiation all day long, storing it like massive batteries. At night, they release that heat, keeping cities significantly hotter than the surrounding countryside. We have accidentally engineered our habitats to trap heat because we ignored the physics of color. So when we look at nature, we see that biology has mastered this balance. Polar bears have white fur to blend in, but their skin underneath is actually jet black. This allows them to absorb whatever scarce sunlight penetrates their fur to stay warm. Zebras use alternating black and white stripes to create microcurrents of air that cool them down and disrupt the vision of predators. Nature never chooses a color by accident. It is also important to realize that our eyes only see a tiny fraction of the story. we only see the visible spectrum, but heat is often transferred in the infrared spectrum, which is invisible to us. A shirt might look white to your eyes, but could be dark in the infrared spectrum, absorbing heat in ways you cannot see. This is why modern athletic gear is engineered not just for visible color, but for infrared performance. This leads us to a philosophical realization about our existence. We are not isolated entities. We are in a constant exchange of energy with our environment. We are thermal engines, constantly trying to maintain a precise internal temperature while the universe tries to freeze us or cook us. The clothes we wear are the interface between our biological engine and the cosmic furnace of the sun. So, the next time you are standing in front of your mirror, deciding between the black shirt or the white one, remember that you are making a scientific calculation. You are predicting the weather, assessing your activity level, and deciding how much solar radiation you are willing to invite into your body. You are not just getting dressed. You are calibrating your interaction with the universe. If you want to stay cool and stable, you choose white. You choose reflection. You choose to shield yourself from the chaotic energy of the star. You want to warm up, or if you need to dump heat quickly after sunset, you choose black. You choose to open the floodgates and let the energy flow through you. Both strategies are valid. It simply depends on the quest you are undertaking that day. We often think of science as something that happens in a laboratory with beakers and lasers, but science is happening in your laundry basket. It is happening in the paint on your walls. It is happening on the asphalt of your driveway. Understanding these principles gives you a slight edge, a way to navigate the physical world with more intention and less suffering. That is the power of knowledge. If this deep dive into the physics of color changed how you see your own wardrobe, hit that like button and share this video. Share it with someone who always complains about the heat but insists on wearing black. Subscribe to Questhut because our next quest digs even deeper. Until then, choose your colors wisely, respect the sun, and keep exploring. See you, Questers!